Imagine you're building something where speed is just absolutely everything. Maybe a high-performance simulation or like a core part of a game engine.
Right, where every nanosecond counts.
Exactly. So how do you manage big collections of data with total precision without losing any speed?
And that's where C++ arrays really come into their own.
Yeah, and that's what we're diving into today. We've been looking at Professor Jerry Sietsoy's YouTube lectures, C++ arrays part 1 and part 2. Really insightful stuff.
hmm
We want to pull out the key ideas for you on this, well, foundational C++ concept.
That's the plan. Our mission today, really, is to cut through any confusion and give you a clear, structured picture of C++ arrays.
Okay.
We'll cover, how they're set up in memory, the different kinds you might use, how they work with functions, all that.
And why they work that way.
Exactly. The why behind it, not just the what. So you can actually use them effectively, manage data efficiently in your own code.
Okay, so let's get right into the core of it then. The sources define an array as a collection of fixed number of elements, all of the same type, and in contiguous memory space.
Right.
Now that phrase, contiguous memory space, I admit when I first really thought about that, it made me pause. Can you maybe unpack that a bit? Why is that part so critical in C++ space?
Oh, absolutely. It's kind of C++'s secret weapon for raw speed.
Okay.
See, when you declare an array, the compiler sets aside one single unbroken block of memory for all the elements.
So no gaps?
No gaps. Think of it like a row of storage lockers maybe right next to each other.
Right.
There's a starting point, the base address. Let's say memory location 1000, just as an example.
Right.
Now, if you have an array of integers, and maybe each int takes 4 bytes.
Okay.
The first element is at 1000, the next is right there at 1004, then 1008, and so on, just lined up.
Ah, I see.
And because they're contiguous like that, C++ can figure out any element's address incredibly quickly.
How does it do that?
It just takes the base address, adds the index you want times the size of each element. So base address plus index element size, boom.
Wow, okay. That's direct.
Super direct, lightning fast. It's a huge reason you choose raw arrays when performance is absolutely critical. Your CPU can even grab multiple elements at once because they're all together like that, much faster than if the data was scattered all over.
That makes total sense. Direct access, no hunting around. And key to using them is that zero-based indexing, right?
Yeah.
Array is the first one,
Always starts at 0.
and array size 1 is the last one, which brings us straight to inbounds versus out of bounds.
Crucial concept.
Because going out of bounds, like trying to access cool student 3 in an array that only has size 3.
Yeah, index is 0, 1, and 2.
Exactly. Index 3 doesn't exist. And trying to access it isn't just, maybe an error message in some newer compilers. It's a real runtime danger.
Oh yeah, big danger.
You're basically accessing memory you didn't intend to access, as the source puts it. Could be anything out there.
Could crash your program, corrupt your data. Unpredictable stuff.
It's one of those classic C++ things that really teaches you to be precise, doesn't it?
It really does. It's fundamental. And speaking of being precise and how structured they are, it makes you wonder, can you just copy one whole array to another? Like just array A, array B?
Yeah, I've wondered that too. What's the deal there in C++ thing?
The answer is a definite no.
Oh.
And, it's a very deliberate design choice.
Ah, okay. So it's on purpose.
Completely. The rule is there are no aggregate operations for raw arrays.
Yeah.
If you want to copy array B to array A, you have to do it element by element.
One at a time.
One at a time. Usually in a loop. It's not an oversight. It's C++ forcing you to be explicit about copying that chunk of memory.
Right. It avoids hidden costs or maybe accidentally just copying the address instead of the data.
Exactly. It fits that whole C++ philosophy of you don't pay for what you don't use. You're in control. Professor Soy even had that memorable example about Draco being a bugger, where it showed assigning one element within the same array to another position, like houses 0, houses 2. Even that is an element-by-element copy. It's always single-element operations.
Okay, so that nails down the basic structure and some, well, not limitations, but deliberate design choices for single-dimension arrays.
Right.
But data isn't always just as simple, is it? What happens when things get more complex? How do arrays handle that?
Yeah, good question. That's where we get into different types or structures of arrays.
Okay.
First up, you have parallel arrays. It's a simple idea, really.
Right.
Just 2 or more separate arrays where the elements at the same index are related.
Like one array for names, one for grades.
Exactly like that, like columns in a spreadsheet almost. You've got student ACZ corresponding to student grades. Same index links the related data across the arrays.
Got it. So synchronized lists?
Pretty much. And then building on that, you can actually have arrays with more dimensions.
Like
Precisely. The most common one you'll see is the two-dimensional array, perfect for anything that fits naturally into rows and columns, like a game board, a matrix, you name it.
And how do you declare that?
It's data type of random arrows columns, so 2 census square brackets. The first index usually represents the row, the second is the column.
Okay. And can you go beyond 2 dimensions?
You can, yeah. It's less common, but C++ allows it. You just keep adding brackets. Data type named dim2, dim3, however many you need.
Right. Now, Professor Soy's sources had this brilliant example combining some of these ideas, didn't they? The house cup one.
Oh, that was a fantastic example. Yes, it really showed how you can combine a two-dimensional array with a parallel array very effectively.
And they used enums, too, which I thought made it super readable.
Absolutely. They started by defining enum house type.
With Gryffindor, Ravenclaw, Slytherin, Hufflepuff.
Right, and another enum category type for things like honesty, integrity, attendance, academics, Quidditch. Much clearer than just using raw numbers like 0, 1, 2.
Definitely. So what was the array setup?
Okay, so they had the main 2D array, int house cup number on house's number of categories. That held all the actual scores.
Rows for houses, columns for categories.
Exactly. But then, to make the output friendly, because you can't just print Gryffindor from the enum directly.
Ah, right.
They used a parallel array, string name houses, number of houses. And that held the actual strings, Gryffindor, Ravenclaw, etc.
Clever. So you link the score data to the printable name using the index.
Precisely. And then they showed assigning some scores manually, I think, for Gryffindor.
Yeah.
And then using loops to get input from the user for the other houses, which involved using Staticast too.
Why was that needed again?
Well, when the user types in a number representing a category, you need to convert that plain integer back into the specific enum category type to use it safely as an index or identifier. Staticast does that conversion explicitly.
Okay, makes sense. Robust code.
And finally, they looped through, calculated the total score for each house from the 2D array, and printed it out next to the house name from that parallel name houses array.
It really tied it all together nicely, didn't it? 2D arrays, parallel arrays, enums for clarity.
Yeah.
Very practical.
A brilliant demonstration, yeah. Shows how these concepts work together in a real-world-ish scenario.
So we've got the definitions, the different structures, but knowing what they are is one thing. Using them well in a bigger program, especially passing them to functions, that's where the rubber meets the road. And C++ arrays have some pretty specific rules there, don't they? What's the main thing to remember about passing arrays to functions?
Right, and this connects directly back to that contiguous memory thing we started with.
Oh, okay.
The absolute key rule is, for arrays, functions are passed by reference only. Automatically.
So you don't use the usual ampersand end sign?
Nope. You won't need to use the end sign in the function's parameter list like you do for other variables you want to pass by reference. It's implicit for arrays.
So the function is always working on the original array, not a copy.
Always the original. It's like you're handing the function the actual address, the starting point of that memory block. It's not making a copy of all the data, which would be inefficient for large arrays anyway.
That makes sense, especially given the focus on performance. Okay, so if they're always passed by reference, does that mean a function can return a whole array?
Ah, good question. If we connect that thought, it actually leads to the opposite conclusion.
Oh.
Yeah. Functions cannot return a value of type array.
Can't return them? Why not?
Again, it comes down to that idea of aggregate data. We mentioned earlier we can't return aggregate data directly. Functions in C++ are generally designed to return single values, like an int, a double, a pointer.
Or work via references.
Exactly. So if you need a function to, say, fill an array with values, you don't have the function return the filled array. Instead, you pass an existing array into the function by reference automatically, and the function modifies that original array directly.
Okay, got it. Passed by reference can't be returned. So with those rules in mind, how do we actually declare them in the function parameters? Because I know it's not always just data type array name size. It gets a bit different there.
You're right. There are specific syntax rules you have to follow. For a simple one-dimensional array, the size is actually omitted in the function parameter list. You'll typically just see data type array name, empty square brackets.
But if the size is omitted, how does the function know how big the array is? How many elements to work with?
Ah, that's the catch. You must pass the size, or at least the number of elements you want the function to process.
Right.
and a separate argument, usually an integer parameter right alongside the array parameter.
Okay, so my function, my array in array size, something like that.
Precisely. Now, for two-dimensional arrays, it's slightly different.
How so?
You must specify the size of the columns, the second dimension.
Must specify columns, but not rows.
Correct. The first dimension, the rows, can be omitted, like with 1D arrays, but the column size is essential. The compiler needs it to calculate the memory offset correctly when you access elements like my2DeRoCol.
Right, because of the contiguous memory layout, it needs to know how long each row is to find the next one.
Exactly. And that logic extends to multidimensional arrays if you have more than 2 dimensions.
Let me guess. Only the very first dimension can be omitted.
You got it.
Yeah.
Only the first dimension can be omitted.
Yeah.
All the others, the second, third, fourth, whatever, must have their sizes specified in the function parameter declaration.
Okay, that's a clear set of rules. I remember Professor Soy had that simple Hogwarts houses example again, but refactored using functions. How did that illustrate these points?
Yeah, that was a neat little refactor. Perfect illustration. Originally, it was just code in main to enter some house names into an array and then print them out.
Right.
The refactored version broke that into 2 functions. Something like void initialize array, string list, int list size, and void print array, string list, int list size.
Ah, so you see the list with omitted size and the separate list size integer being passed.
Exactly. It perfectly shows those rules in action. The functions know how many elements to process because list size is passed explicitly.
And it makes the code cleaner, too.
Much cleaner. That's really the takeaway there. Using functions like this is just good practice. It keeps your main function tidy, makes the code modular, reusable. It avoids that trap of having, as the source put it, everything up in main.
Which gets messy fast.
Very fast.
Yeah.
This is about writing code that's easier to understand, maintain, and debug. It's fundamental software engineering practice, really.
Okay, this has been, well, quite the deep dive into C++ arrays. Let's just quickly recap the main things we've covered.
Sounds good.
We started with the core idea. Arrays as these fixed-size collections, same data type, all stored right next to each other in memory, that contiguous block. Key for performance.
The contiguous part is vital.
Then, the crucial zero-based indexing. Index 0 is the start. And staying in bounds is non-negotiable to avoid nasty runtime problems.
Definitely. Watch those bounds.
We also hit that important C++ restriction. No aggregate operations. You copy arrays element by element. It's deliberate, for control.
Right. Explicit control.
Then we looked at different structures.
Yeah.
Parallel arrays for linking related data across separate arrays.
Like names and scores.
And multi-dimensional arrays, especially 2D ones, for grid-like data, and how enums can make indexing them much clearer.
Yeah, house cup example.
And finally, how arrays behave with functions. They're always passed by reference, automatically, no unmeted.
But they cannot be returned by function.
Right. And those specific rules for declaring them in parameters: omit the size for 1D, pass size separately, omit only the first dimension for multi-D, specify all others.
You've got to remember those details.
Absolutely. Understanding these building blocks, it feels essential for anyone seriously learning C++ or even similar languages where memory layout matters. It impacts how you write efficient, solid code.
It really does. So here's something to think about now. What really stands out to you? We've focused on these classic C++ arrays, fixed size, contiguous memory, super fast access.
Yeah.
But think about that fixed size nature. What are the trade-offs? How does this very strict, rigid organization compare to maybe more flexible containers you find in modern C++, say, like std.vector or even std.array, which adds some safety?
Right. Or containers in other languages.
Exactly. What's the balance point between that raw, predictable performance of C-style arrays and the kind of dynamic adaptability you often need for real-world data that might grow or shrink unexpectedly? Where do you draw the line?